In this recording, we'll be talking about all of the factors that affect the image. But first, let's talk about the stages of the image. There are really two different stages that we're going to consider that the image undergo. First is the latent image. This is the image that before you can actually see it. So it's the x-rays have gone through the patient, they have interacted with the different body parts, and now they're carrying that information about those parts to the image receptor, where the image receptor will absorb that information and store it for just a moment. So that is the latent image. Latent means before it can be seen. So the second stage is the displayed image. So the displayed image is the image that you will actually see on the monitor. So it's the latent image that has undergone several different digital image processing techniques. We're going to discuss what those are at a later time, a little bit today, and then some more as we move through the semester. So we have the latent image. The x-rays have gone through the patient. They have interacted with tissue. They've carried the information towards the IR. The IR absorbs it and stores it for just a moment. And then once the IR is ready for processing, it will send all of that data off to the processing computer, where the computer will take that information and apply varying processing techniques to display the image as you would expect to see on the monitor. So here is an example. So in this example, I have a patient's wrist lying upon an IR. So we'll have the x-rays go through the wrist. The photons will enter the patient part. Then the photons will interact with that bone, that soft tissue, maybe some ligaments and whatnot, and then it will go into the image receptor where it will hold it for just a moment. So we'll have some IRs, kind of like we've talked about in lab, like the PSP plates. It will store that information until I take that PSP plate over to the reader, where the reader will extract that information off of it. Or like the FPD plate, the FPD system will convert that x-ray energy in two different ways, either direct capture or indirect capture. We'll talk some more about that. But now that information is being converted and processed, and then it will then become the displayed image. So in this example, here's our wrist again. So we've had the x-rays, they've gone through, they've struck the different structures within the wrist, and now we have this image with bone, soft tissue, some, the skin, the muscles, some ligaments. We can see those varying things, and you can also see that the patient had a ring of some sort. So all of these would be considered the displayed image. So let's break this down even further. We're going to talk about some characteristics of each of those types of images. The first set we're going to look at is the characteristics of the latent image. So we have two: receptor exposure and subject contrast. So the receptor exposure is simply the amount of radiation that strikes the image receptor. And then subject contrast, again, we've kind of talked about this some, the difference in radiation intensities due to the attenuation characteristics of the different tissues in the body and contained in the remnant beam. So with our wrist x-ray, we had some bone, the soft tissue, so we had the subject itself is going to lend some contrast to our image. So that bone, that tightly bound with calcium, and then we have the soft tissue, a lot of water, so it's more loosely bound. So we're going to have the KVP, the photons, are going to interact differently in those different tissues, giving us the subject contrast. So let's talk a little bit, just briefly here, about receptor exposure. The image receptor exposure is determined by the KVP, the mass, the body part, and how the image receptor forms the image. We're going to talk in a little bit. I'm going to say a lot of depth. We're going to talk in a little bit more depth as we talk about each different type of image receptor. So we're going to talk about PSP. We're going to talk about the different types of FPDs, the different technologies, the different capture technologies that we're using, and we'll talk about how those different detectors will determine the receptor exposure. We will also talk in some generic terms about some standardization that is trying to come about. It's been a little bit slow coming about, but the physicists are trying to get the vendors to come up with a standard way to display exposure to the IR. One of our systems actually uses it. The deviation index is the standardized version of looking at receptor exposure. When we were talking about mass and kVp this past week, we talked about how they relate to the number of photons that are created within the X-ray tube. Well, as the number of photons increase, the amount of exposure to the IR is also going to increase. So if I double the mass, I double the number of photons coming out of my tube, I double the exposure to my IR. If I increase my kVp by 15%, it in essence doubles the number of photons coming out of my X-ray tube, which should then also double the amount of exposure that my IR receives. The image receptor exposure is measured by an exposure indices. In lab, again, we've looked at the DI, or the deviation index, and with the PSP system, we've looked at the S value, or sensitivity value, or sensitivity number. Each vendor, again, is very proprietary. I wish it were not, but it is. And so when you get to the hospital, you'll just have to figure out what their systems are using and learn that system. All right. One more try here at subject contrast, just to give us a little bit more. Because the subject is made up of so many different objects of varying atomic number, varying atomic mass density, our kVp is going to help in the recording of those different varying tissue types. So think of it in this way. If I use an X-ray beam of, say, 60 kVp, so I use that 60 kVp beam to image, let's say, the pelvis. So I have this part, I have the pelvis, there's a lot of bone, there's also some soft tissue, and I have bone of varying thicknesses. So with the 60 kVp beam, I have a very narrow range of X-ray photon energies. You know, remember that the average X-ray beam energy is 1/3 of the actual set kVp. So if I have 60, 1/3 of that would be 20. So I would have an average beam energy of 20 keV. And I would have some 60 photons, but not a ton. So I really probably wouldn't have a large number of high energy photons that would be required to penetrate through some of the thicker portions of bone that would be found in the pelvis, like the head of the femur. One of the things we want to look at in a pelvis is being able to see the head of the femur set inside of the acetabulum. So if I don't have enough higher energy photons, it's going to be very difficult for me to be able to distinguish the head of the femur from the actual acetabulum of the pelvis. So I would rather have a beam that has a much wider range of energies. So maybe, say, 80, 85, maybe even 90 kVp. So I want something that's a little bit higher, that will allow for my image receptor to distinguish the different tissue types more closely. So that is, in essence, giving me the visualization of the subject contrast. So I want those, especially in this instance with that pelvis, I want to be able to distinguish the head of the femur from the acetabulum so I can see how they are sitting in relation to one another. It's a very important thing for the radiologist and the referring physician to see for that exam. So I get that by having a wider range of energies, those X-ray photon energies, so setting a higher kVp. So now let's talk about characteristics of the displayed image. The first set, we have brightness, the luminance or intensity of light from an area of the diagnostic image displayed on a monitor. Contrast, the visible difference between two adjacent areas of brightness within the displayed image. And then grayscale, the range of brightness levels or pixel values within the displayed image. We touched on these three this past week in lab. We talked about what brightness meant and how that related to the technical factors we were setting, and then also contrast. Just talking about subject contrast, we kind of delved into the visible part of that, being able to distinguish two different areas from one another. So that I would need a lower contrast image to see the differences in this very subtle differences between what, using our last example, that head of the femur and the acetabulum. They're very close in composition, but when I have a wider range of photon energies available to me, I am more likely to be able to distinguish those very subtle differences in those two structures. So that would give me what I would call a low contrast image. Higher KVP is going to give me a lower contrast image, lower subject contrast image. And then the lower KVP is going to give me a higher contrast image or higher subject contrast image. I know that sounds weird, but the more you look at these images, the easier that will become for you. Then we have noise. We talked about noise when we were talking about mass specifically, but also KVP has a lot to do with noise also. So the definition of noise is any unwanted, useless information recorded on the image that obstructs the visibility of anatomy or pathology of interest. Noise can be from scatter radiation, which we talked about when we were talking about KVP, and then quantum model or quantum noise when we were specifically talking about mass. But we know that mass and KVP both affect the quantity of photons that are going to be produced by my X-ray tube. Then we have sharpness. Sharpness is an interesting term. It's kind of a difficult one sometimes for folks to understand. And there are a whole lot of things that will affect sharpness. And we'll talk about each of those things as we get to them this semester and next. But the basic definition of sharpness is the abruptness of the edges of an image detail, or maybe a little bit easier to understand, the ability to visually distinguish the edges of objects from one another. You remember when we were talking about that knee this past week in KVP? I believe it was we were talking about penetration. And we had the image on the left was showing us a knee where we could not visualize the patella at all because we didn't have enough KVP, so there wasn't enough penetration for the image receptor to resolve the different tissue types there. And so we were unable to visualize that at all. And then we had the second image that was on the right where we did have the appropriate penetration and we were able to resolve and see the patella in through the femur. That is a form of sharpness, and we'll talk again a lot more about this as we go. But specifically, that one, that what I've just described is contrast resolution. So resolution, sharpness, you'll hear some interchangeable words, and we're going to talk a little bit more about it here in a moment. Then we have magnification, the difference between the size of an image and the size of the object it represents. We'll do some fun labs this week for that one. And then distortion, the difference between the shape of an object in an image and the shape of the actual object it represents. And we'll talk a little bit more about that here in a moment. So let's look at this example for brightness. Again, here's that definition, the intensity of light shown through an object in a digital image on a monitor. So let's start by looking at this image in the center. We're going to call that our optimal image. So in this optimal image, we can see the trabecular patterns, we can see the different structures, we can see the head of the femur sitting inside the acetabulum. So when we change the brightness or we increase the brightness, literally it just increases the intensity of light coming through. You'll notice though, sometimes you lose a little bit of the detail you had before in that optimal image when you increase the brightness to a particular level. So you have to be kind of careful when you're manipulating, because this is a post-processing technique that changes the brightness of the image. And I also need to mention here, brightness is a function of the monitor also. So different monitors will give off certain brightnesses. So right now, I want us to stick with the post-processing of what brightness appears to us. So here in the image on the right, you'll see where we have decreased the brightness of the image. The overall image has gotten darker. So we have decreased brightness in that image on the right. Again, you can start seeing a few different structures that maybe you didn't see in some of the others. Good and bad and different. I think a lot of times the radiologist will actually change the brightness of the images at their workstation when they're looking at different structures within the image. So it is not changing brightness is not a bad thing. It's actually something that's extremely useful for our radiologists so they can see the different structures in the different lights. All right, we've talked about contrast a little bit before this past week, but I wanted to show you this particular example. So again, contrast the visible difference between two adjacent areas of brightness within the displayed image. In this image on the left, you'll notice this is your typical chest image. You can easily pick out the scapula on both sides. I can see all the structures, the body structures, the clavicles, the ribs. I can see the heart, the diaphragms, costophrenic angles here in the edge. And then I also notice here in the spine, I can see the disc spaces pretty well through the heart shadow. And I do notice that there is some sort of object, some clothing artifact on this image. But when I change the contrast of this image, all I've done is increase or lengthen the scale of contrast visible in this image. I have made this image on the right lower contrast, meaning I have very subtle differences in gray values visible to me, whereas over here in the image on the left, the differences are not as subtle. I see blacks, I see whites, and I see some grays. But then the image on the right, I see a lot of grays. I still have some whites, I still have some blacks, but I have a whole lot of grays in between. Which is it's interesting because you now see those bra clips down the center of this patient much more apparent than in the first image. So your typical contrast, the visual contrast of the image on the left is not good and it's not bad. It's what's typical. The image on the right, again, it's a longer scale of contrast, which is not good, it's not bad. It's just allowing me to see the different structures in kind of a different view. Again, this is something the radiologist will do on a daily basis when they're looking at images, because this allows them to see different structures, with different gray values. And sometimes you can pick out very subtle changes by just changing the brightness and or the contrast in the image. And it's easier for the radiologist to make a definitive diagnosis when they can do that. Grayscale. So grayscale is an interesting term. I think I prefer grayscale often when I'm trying to explain this to students than contrast. Contrast can kind of get convoluted and hard to explain. To me, grayscale is easy. The equipment is inherently equipped, I guess you could say. It will use a particular bit level, and we're going to talk about this more later. But basically, each modality will have a bit level of which they will use to acquire their images. And it's most of the time it's a set bit level. You can't change it. It just is what it is, and different modalities will use different levels. Well, basically what that bit level is doing, it's saying how many shades of gray will be available during the image acquisition process for that modality. So you might say, well, why wouldn't you want the higher bit levels, the 10, the 12, the 16-bit levels? Well, those are great because I can see a whole lot of gray values. But also, as I increase the bit level, I'm increasing the physical size of my image, so the file size of my image. And just like trying to, download a PowerPoint at your house. Sometimes those PowerPoints are enormous, especially if they have a lot of image data and a lot of slides in them. It takes a really long time to download those images. Now think about trying to speed images through a hospital with lots of other data going on. The higher the bit level, the bigger those images, the slower they're going to move through the physical wiring of the hospital. So lots of things have to be thought about. And there's at a point that it doesn't matter, once you get to a certain bit level, going higher probably isn't going to change how the radiologist is going to read it or their ability to read it, actually. You can only visually see so many shades of gray with the naked eye. So at some point, it just doesn't matter how many bits. They could have, 2,000 bit and it wouldn't matter because we couldn't resolve that many shades of gray anyway. So somewhere in between, 8, 10, 12 bit, and usually use the higher bit levels like 16-bit for mammography because the tissue is so very similar, and so they need all of those subtle changes to pick out any changes in the breast tissue. Noise. Pretty simple topic to wrap your brain around. Any unwanted, useless information recorded on the image that obstructs the visibility of anatomy or pathology of interest. So in this example, this is pretty easy to see. You can see that the top image is very mottled in appearance. Got lots of dots, lots of areas that the computer is having to figure out what might need to go in that area of the image. We looked at it last week and I showed you a couple of images. But this one, it's very easy to see, especially soft tissue. You can really see it in the bone. You lose the ability to resolve the trabecular pattern, whereas the image in the bottom, you see lovely trabecular pattern lines. And the image in the top, it's very difficult to see those. So this particular image was due to not enough mass, so not enough photons reaching my image receptor to create my image. But like we talked about last week, if the computer kind of knows what it should look like, so it will try to make up the information that's missing. It'll see an area that doesn't have a whole lot of exposure in it, and it will start just looking at the neighboring pixels, neighboring area of the image, and just make it up. That's why it looks very dotted in appearance, whereas the nice smooth lines of the bone and trabecular pattern here. So now that we've kind of talked about those particular characteristics, I want to, before we hit the next ones, I want to talk about the anatomy of an image in very generic terms. You have two terms used to describe an image. And when I talk about an image, in this instance, I'm going to take this into the astronomical world. When we look at the moon and the sun, when we do the eclipse, we're seeing those structures, but we're seeing the actual shadow. So the umbra portion of the image, or portion of the shadow, is the area that is completely blocked out by light from the source. So when we're talking about X-rays, we're talking about that area of full attenuation of the X-ray photons, or the full blocking of the object within that X-ray image. And then penumbra is the shadow that kind of surrounds that umbral image. You'll see some light getting through and some will be absorbed and blocked by the object. It's kind of that fuzzy area around the image. So I've come up with just kind of a drawing to represent and kind of show you umbra and penumbra. I usually do this in the classroom. I'll get a flashlight out or I'll use my cell phone, and I will use my hand, and I will just have my hand against and shine the light from my hand to the wall. And when I have my hand fairly close to the wall, or in this instance a ball, you'll see a good umbra of the image and very little penumbra. The penumbra, again, is that shadow beyond the actual object, the representation of the object being imaged. Again, here's light waves hitting the object. As I move my ball towards the source of light, in this instance, one, my object will now appear magnified, and then my penumbra portion of the image will grow exponentially. And that penumbra portion of the image has very fuzzy edges. So I have the umbral part of the image is a more distinct line. You can see that object very clearly when I have more of an umbral image than a penumbra. As the penumbra grows around the image, and most often occurs through magnification, I will see more fuzzy. It will be a little bit more difficult to discern the actual edges of the umbral image versus where the penumbra starts and stops. So now that we kind of got those terms down, let's look at some of the geometric properties that we use in. So the first thing we're going to look at here that has effect over geometric properties is the focal spot. We kind of talked about this when we were touching on the X-ray circuit and when we were talking about mass. But if you remember the difference between the small focal spot, large focal spot, and then what their actual focal spot size was versus their effective focal spot size, you will remember that with the larger focal spot, I have more pronounced divergence of my beam. So I have more divergence of my beam on the edges. Thereby, when I have those photons going off at a greater angle, I have the possibility that because those photons are angled, they could record the object or the anatomy of interest at an angle and thereby create some distortion. They call that focal spot blur. So focal spot blur. Truly, it's very difficult to see the difference between the focal spots. Now, maybe in the past when they had, very large focal spots because of the type of target they were using, this might have been a bigger factor on the sharpness of the image. But with today's equipment, I would challenge anybody to actually see the difference between using the small focal spot and the large focal spot with the digital techniques that we have today. So in general, the rules are, as a technologist, you should always choose the smallest focal spot that makes sense for the part that you're imaging. So therefore, usually we would want to use a smaller focal spot on extremity exams. I would tend to use a larger focal spot on the thicker body parts, because remember, we want to spread the heat of those exposures over a larger area of the anode, so therefore I would want to use a larger focal spot for that. But honestly, I can't even tell you that I have ever seen the results of focal spot blur. However, this probably will be a question that could come up on your registry, so you need to understand that in theory, the smaller focal spot is going to produce less focal spot blur, or a smaller penumbra around the image. So a sharper image, you could say, would occur with the smaller focal spot than the larger focal spot. And here's a picture depicting that. You can see that the larger focal spot is going to create a larger area of unsharpness or a larger penumbra than the smaller focal spot. And, we talked about the anode heel effect, but remembering that the anode angle, again, we can't change it. It is what it is. But let's see, the beveling of the anode angles that are steeper than 45 degrees will cause the effective focal spot to be smaller than the actual focal spot. So the steeper the anode angle, the smaller the projected focal spot, and therefore greater sharpness of recorded detail. So, but again, with the steeper angles, you're going to have more visible anode heel effect. So the anode heel effect is more visible with steeper angles, larger focal spots, shorter distances, longer or larger field sizes. So basically, if you set up with a steep anode angle and you use the large focal spot and you use less than 40 inches, 30, 25, and you had it wide open as far as it could go, you might possibly see the effect of the anode heel effect. Again, we'll do some, we'll do some experiments in lab to see if we can see it, but it's highly doubtful that we will actually see the effect of the anode heel. And here's just a line drawing showing that same thing we just talked about. So just one more time to keep this in your head, the intensity of the beam is greater towards the cathode end of the tube. So therefore, we want to put the thicker part under the cathode, thinner part under the anode to take into consideration any help we might get from the anode heel effect. All right, let's go into sharpness a little bit. So again, sharpness, the ability to visually distinguish the edges of the objects from one another. So in this example, look at the center image. I have nice trabecular pattern. I can see my patella through my femur. I can see nice articulations here between the tibia and the fibula. In the image on the left, it just looks blurrier. Okay, it's a softer looking image. I still can see some of the trabecular patterns, but definitely not as abrupt as I can see them in the center image. So I would say that the image on the left is not as sharp as the center image. Now let's look at the image on the right. I have very strong edges. I see it's very distinct. I mean, look at the patella. You can really see that patellar edge, whereas I can see it here. It's very blurry here. So this is, appearing, the edges are just a bit blurrier. This effect is strictly from digital processing, nothing else. This is actually the exact same exposure. I just manipulated this middle image to show you blur, a little bit of blur from changing the, it's an edge enhancement or smoothing. This is actually a smoothing technique, whereas this is an edge enhancement technique where I am asking the software to look at this image and really draw out the edges of all the structures within that image. Digital processing all the way. Has nothing to do with how I took the image, nothing about the patient, nothing at all. It is strictly what I can do on the back side and change the overall look of the image. We're going to talk some more about this later down in the semester when we're talking about digital processing. Magnification. So magnification, we talked about that here, earlier when we were talking about the penumbra and the umbra, where the second image I had the ball closer to the flashlight, therefore it looked magnified on my wall, my image receptor. So in essence, that's what you're seeing here. These three images were taken to demonstrate what happens when you magnify and change the OID, the object to image distance, and don't change the SID and then compensate. So we'll do this experiment actually in lab. So here's my control image. This is my knee that is right next to my image receptor. This is that same knee where I have increased the object to image receptor distance. Therefore, and I did not change the source distance, the source to image distance. So therefore I get magnification. And then in this image, I have kept the same object to image distance, but I have compensated with my source to image distance. These aren't the best looking images because there's some, some digital stuff that happened to them, but you can definitely see the magnification, and you can definitely see how when you magnify it, I get a little bit of blur right here around the edges. In this image, you can now see the finer details a bit better than I could in the magnified image. Even though it looks a little smaller, I can still see the details a little bit better because I have compensated for that increase in object image distance by increasing my SID. So in essence, in this far right image, I have reduced the penumbra that is visible in the middle image. So I have increased the distance from the source to the image receptor and thereby reduced the appearance of the magnification. And in that same realm, I have then decreased the amount of penumbra that is visible in my image. So let's break down these different distances. Let's start with the SID, or source to image distance. We measure the source to image distance from the focal spot down to the image receptor. So whether that image receptor is on the tabletop or if that image receptor is put into the bucky, you always need to make sure that you measure to the image receptor. So the sharpness, or the recorded detail, will be improved in direct proportion as the SID is increased. So here's my best example that's kind of ridiculous. But say in a chest X-ray, I want to see the heart. That's one of the things that I want to visualize in my chest X-ray. So which is why we prefer a PA chest X-ray in lieu of an AP chest X-ray. The PA chest X-ray puts my heart closer to my image receptor. So with it being closer to my image receptor with the patient in a PA position, I am able to reduce the object, the distance from the heart to my image receptor. So the object to image receptor distance. So I do that by doing a PA chest X-ray. If I turn my patient and I do an AP chest X-ray, I now have my heart farther away from my image receptor. Therefore, I will have magnification of the heart. The only way I could get my heart, even better than doing a PA, is to snatch it up out of the chest and put it directly onto the image receptor. That's not possible. So I will put the patient in a PA position. That's why I increase my SID, so I can compensate for some of that object to image distance. So I move my SID back, therefore it's going to reduce the visualization of magnification of the heart because of that increased OID, and by increasing the SID. All right, let's look at this visual here. So we have, again, our SID is measured from the focal spot to my image receptor. My object to image distance, which we'll look at here in a second, is here's my object to my image receptor. And then they also have a source to object, or SOD, source to object image distance. You know, in my chest X-ray, that's, you know, I can shoot a chest X-ray at 40 inches, but the radiologist is used to looking at those images at a 72-inch SID, and they expect the heart to be a certain visual size when they pull up those images. So when you are not consistent in your SIDs, it can kind of throw the radiologist off sometimes, because they are used to visually seeing the heart in relation to the lungs and the diaphragms and the spine and the ribs at a certain magnification level. So, but in essence, we use the 72-inch SID because I cannot snatch the heart up out of the chest and put it directly on my image receptor. That would defeat all purposes of trying to take a chest X-ray on a live patient. So, that there's, again, like I said, there's reasons why we do everything and why the method to the madness. And you'll see a chest X-ray at 72, but then you'll do ribs at 40 inches. I'll let you ponder that for a little bit. All right, so here let's look at the relationship between OID and SID. So when I have the OID set at a particular distance, okay, so here in this one I have, I don't know, whatever that, we'll say that's, I don't know, 20 inches. So my object is 20 inches from my image receptor. And here is my 40-inch SID. So I will have a larger area of unsharpness. And notice how my area of unsharpness is greater on one side than the other. So which one is it going to be greater under? The cathode. Yep, the cathode. So the cathode end will show me, will display a greater area of unsharpness at those shorter SIDs. So I leave my object to image distance because it is what it is. If I increase my SID, what that does is decreases my area of unsharpness. And in essence, it's also, you're going to find that it's going to decrease the magnification of the object. So, I think we kind of talked about this. What's the primary reason for doing a chest X-ray, PA, at 72 inches instead of AP at 40 inches? Well, I want to reduce the magnification of the heart. So I will turn the patient, so I'm taking a PA, and increase my SID. Therefore, I am going to decrease the magnification that's going to naturally occur of the heart. So, SID. SID does not distort the shape of the object at all. It will only magnify. There are many other factors that distort the shape, and we'll talk about those here in a moment. But increasing the SID does reduce the intensity of the exposure. You remember we did the inverse square law, talking about the exposure, or the occupational exposure, the milliroentgen exposure to the person. You know, at a particular distance, say 2 feet, I get an exposure of 100 milliroentgen. When I move back to 4 feet, I now am reducing my exposure by 4 times. Remember, so I would then have just an exposure of 25 milliroentgen. Well, think about that for a minute. If just by increasing, or reducing my, increasing my distance from the patient will reduce my exposure, what do you think is going to happen to the intensity of the X-ray beam that's going towards your patient? If I increase my distance, it's going to decrease the intensity. So that's why when I was, kind of tongue-in-cheek saying, we tell you you have to do this at 40 inches. We tell you you have to do this at 72 inches. In essence, you could shoot everything at 72 inches if you wanted to. You could shoot everything at 100 inches if you wanted to. It just doesn't matter. You have to then, if you do that, you have to figure out how to modify your exposure factors so that you still have enough photons reaching your image receptor. So I can shoot everything at 100 inches. I just have to use this theory of how the intensity of my exposure reduces. All right, let's look at a couple of examples. We've looked at some before, but let's look at these and actually, because we're going to need to use the formula that was on the previous slide. The first one we really don't. What is the intensity of the beam at 36 inches if the intensity is 8 milliroentgens at 72 inches? Well, honestly, because that is a true doubling or halving of distance, that's a pretty easy one to do in our head. We know if it was 8 milliroentgens at 72 inches, I'm halving my distance to 36, then it's going to change the intensity of my beam by 4 times. So I'm actually going to have 4 times the amount of exposure at 36 inches than I did at 72 inches. So therefore, the answer on this first one is 32 milliroentgen. The bottom one, however, I'm going to really need to use my formula because now I am going from, for 272 inches. So it's saying what is the intensity of the beam at 72 inches if the intensity at 40 inches is 10 milliroentgen. So 40 inches would be my first distance, my SID1, and 72 inches is my SID2. So I'm going from 40 to 72. My original intensity at 40 inches was 10 milliroentgen. The key thing to remember here is this is the square law, inverse square. So don't forget to square the distances. That's probably the biggest mistake most people will make. So when I work the problem out, I square those distances and multiply that by my original intensity. My intensity at 72 inches is now 3 milliroentgen. So I threw in this image. The picture's not great, but it's the best images I have to kind of show you the visual differences between a chest X-ray at 72 inches and a chest X-ray at 40 inches. So you see the heart shadow appears much larger than at 40 inches than it does at 72 inches. You also notice that my positioning has to be very spot on, or at 40 inches, I have the possibility of cutting off some lung field there. So not only is our change in SID from 40 inches to 72 inches helping the heart magnification, it's also going to help magnification on everything else. And you'll have a much higher probability of not cutting off those apices and the costophrenic angles and then the both edges of the lung fields at the 72 inches because we're going to reduce that possibility of magnification. So when we change our distances, when we change our SID, those first questions was we were talking about the intensity of the X-ray beam. Okay, but intensity, I mean, we care about it. Sure, we care about it, but it's not a factor that we can set on our console. It's not something that I can directly go over and tweak something and say, other than changing my distance, say that I'm changing the intensity of my beam or the intensity of the exposure. Now, what I can affect is the changing of my mass and kVp. Typically, changes in distance you will change your mass rather than your kVp. Now, can you change your kVp? Sure you can. But we're going to work these problems in changing our mass. We're gonna say we're gonna leave our kVp alone for right now. We'll bring that into the equation here in a bit. But first, we want to work these as if we're going to leave our kVp alone, and the only factor we're going to look at is the mass value. So you'll notice that this formula looks somewhat similar to our intensity formula. The one thing I want you to make sure you go back and look at is we were using to look at the intensity of the X-ray of the exposure. We were using the inverse square law. Okay, the inverse square law. Now we're going to be using the direct square law to maintain the exposure to our IR. Therefore, our direct square law is going to allow us to manipulate our mass value when we have a change in SID. So this is what the formula looks like. So direct. 1, that's what this means. In the inverse square law, when we were talking about the intensity or the intensity of the exposure, you saw the SIDs flipped. We had SID2 over SID1 squared. That is the inverse square law. Don't get them confused, because you'll get the problem wrong. You'll have the wrong mass value. So make sure you pay close attention to this, that this is the direct square law to maintain the amount of exposure to our IR when we are changing SIDs. This is a great formula to know. Hint, hint. Okay. All right, so let's put this formula into action. If the original technique at 40 inches was 70 kVp at 24 mass, what would be the technique at 72 inches? Well, let's look at our formula. We have mass 2 equals mass 1 times SID2 over SID1 squared. So plugging that information from the question into the formula, we have 24 mass times 72 inches. That's where we're going to. And we came from 40 inches squared, so we worked the math out. Our mass 2 comes out to around 77.76, or maybe 78. Probably, though, we would set either 80 mass or maybe 75 mass. Those are the ones that will be available on our machines. So a very, very useful formula when I need to change my distance. Often you're going to have to do this on the fly. I get that. And so you may not have a calculator handy, but the more you do it, the more you will have a way to estimate what those changes would be. You know, I remember, I think I told you all the story. I think I told everybody. I can't remember now. But I think most of you told the story about the student who did portable x-rays. And she went to take a portable chest x-ray on a patient at his home. And he was a hoarder. And she couldn't get the machine into the room where the patient was. So she had to use her best judgment. And she parked that x-ray portable outside his bedroom window, had the IR in there with the patient, had the patient standing up with the IR in, between the patient between the IR and the X-ray tube, and she had to estimate the distance. And using this formula, she was able to then estimate the mass that she needed to create her image. Now, she probably didn't have a calculator, or she might have, but probably she just had to, using her critical thinking skills, work through the math and get to that approximation. Because remember, we have a pretty good range there, and you'll see that our digital equipment allows us to have a pretty good range. So if you understand the theory of how it works, you're going to better be able to adapt to your situations in the hospital. So in this slide, I've given you some estimates. So it'll give you kind of an idea of where, 40 inches is our normal. That's our normal everyday SID for most everything. So if we have to vary that for any reason at all, here's some estimates for you. So if I'm going from 40 to 60, that's going to be about 2.25 times the mass it would be at 40 inches, or 2 times. From 40 inches to 72 inches is about 3 times, or 3.24. 80 is easy, it's a 4 times. From 40 to 30, it's about half of what the mass would have been at 40 inches. So this just kind of gives you an estimation. You're not always going to have a calculator, so having this thought process in your brain will give you kind of an estimation to get started. So sometimes we do want that shorter SID, and most of the time it's because we want to blur out some anatomy that's around the anatomy of interest. So we'll use the shorter SID to magnify the part, and then often we'll use I think I talked to you guys about the sternum, so in the example of the sternum, when I oblique the patient slightly, I'm moving the sternum away from the spine, and I'm going to then use a breathing technique to help blur the ribs out. And when I use that shorter SID, it's going to magnify the sternum. Yes, there will be a little blurring of the sternum, but it's a very difficult bone to image, and so you often need to employ all these tactics to really bring the sternum out from the surrounding anatomy. So now let's turn our attention to the object to image distance. We've spent some time on the SID, so let's talk about the OID. So again, the OID is the object, so the body part, to the image receptor. So object to image receptor. This is a key distance because we want to have the least amount of object to image distance possible. Well, we've kind of talked about that. When we have a larger OID, we have more magnification. With magnification, we have greater penumbra, so less sharpness. OID will not have any effect on any other shape distortions, only magnification. So same picture as before. We have our object to image distance now is different. So we've left our SID the same. So when we have our object to image distance, we're going to have greater areas of unsharpness. When we have less OID, we have smaller areas of unsharpness or less penumbra. Here is an interesting phenomenon with OID. So when I put some distance between my object and my image receptor, I'm actually going to reduce the amount of exposure that's going to reach my IR. It's interesting. This is an interesting concept. Remember, when my X-ray photons go through my body, striking all the different objects in my body, I'm going to have scatter. Scattered X-ray photons from the body will exit and go all different kinds of directions. Some will move in a semi-forward direction. Others will not at all. They may even come back towards the X-ray tube because I'm going to have scatter in all directions. So think about this. When I have an increase object, so my body, to image receptor distance, I'm increasing that distance, and I have those scattered photons coming out of my patient's body. Because of that distance and because of the angle that those photons are coming out, I have a higher probability that some of those are going to miss the IR altogether. That if I had had my patient right in contact with my image receptor, some of those crazy angles would still have been recorded into my image receptor because I didn't have a great distance for them to travel before they're recorded. So when I increase that OID, that distance, I have a good chance that some of those crazy angled photons, because I'm giving them an additional distance to travel, they may travel off and miss my IR altogether. So what that does is actually decrease the amount of scatter that's going to reach my image receptor. And remember, scatter's bad. Scatter's going to cause noise in my image. Scattered noise, we talked about that earlier. So when I increase my OID, I am decreasing the amount of scatter that's going to reach my image receptor, and that's a great thing. But then we have that trade-off. With an increased OID, I have increased magnification of my part. When I have increased magnification, I have increased penumbra. So, guess what? How can I fix that? Well, I fix that by changing the SID. So if I can change the SID in relation to the change in OID, it's going to allow me to now reduce the effects of magnification. So specifically, when I look at this, it's easier. We talk about it talks about it in relation to the SOD, the source to object distance. I don't measure that though. I can easily measure the object, the image receptor. So it's easier for us to talk about this in relationship to SID and OID. So using the same SID-SOD formula, I can just change the SOD to OID, and it's going to give me the same results. So if I have my original SID, I can figure out what my new SID is when I divide my new OID by my old OID. So let's look at this in relationship to a question. If the OID1 is 3 inches and the OID2 is 9, then the OID has increased by a factor of 3. So if my SID originally was, let's say 40 inches. So 40 inches at 3 inches of OID, and now I'm going to 9 inches. So 9 divided by 3 times 40 will now give me my new SID. So if my first SID was 40, my new SID with a 9-inch OID would now need to be 120 inches. So I'm going from 40 inches to 120 inches, but I have reduced the effect of the increased OID because I'm going to reduce the magnification. So because I reduce the magnification, I'm going to reduce the amount of penumbra visible with the increased SID. And I'm also now going to decrease the amount of scatter that reaches my image receptor because of the increased OID. Interesting concept. We can put it into action actually fairly easily. We'll talk about this in lab because I think visually you'll understand it better when I am talking in lab about it, because I'll use your bodies to demonstrate what I'm talking about here. But just remember that with increased OID, I'm going to have increased magnification. So to combat that, if I increase my SID using this SID-SOD ratio or SID-OID ratio, you will reduce the effect of the magnification, thereby creating a more sharp image, an image with less penumbra. All right, let's look at another example here. I've drawn this one out to kind of go beyond the words. But here we have, in our first drawing, we have a 2-inch OID. And our SID is 40 inches. So now we are going to have an OID of 4 inches. What is our new SID? So if we look at this, we have our SID1 again is 40 times our OID2, 4 divided by our old OID2. So 4 divided by 2 would give us 2. So 2 times 40 would give us 80. So our new SID is 80. And to get our SOD, we take our 80 minus the 4 inches. So that would give us 76 SOD. All right. Now this particular formula, you might see one question on the registry about it. I don't really know. It's a required formula for us to teach you, so I teach it to you. But really, you're probably never going to do this in real life because one is it's really not in our purview. But because it's there, I want to make sure and explain it to you, just so you have at least heard it once. And I'm actually going to create a second PowerPoint slide that's going to go back over some of this math stuff, and I'm going to try to actually work several math problems for you in that recording. But magnification factor. So the magnification factor is determining how magnified the actual object within the body is on the image that's displayed. So you can figure out what the object size is by using the image size that is measurable on the digital image times the SOD divided by the SID. So let's look at a question. So if I have a PA chest x-ray, it was performed at 72 inches, 2.2 centimeter nodule was measured in the right upper lobe, estimated to be around 4 inches from the anterior portion of the chest. What would be the actual size of the nodule? Okay, so working the math, we're at 72 inches SID. Okay, we've got to find the SOD. Well, in the question it says that the nodule is estimated to be 4 inches from the anterior portion of the chest. So the anterior portion of the chest is directly in contact with my image receptor. So I'm going to say that my OID of that nodule is 4 inches. So I take 72-inch SID minus the OID of 4 inches, and it's going to give me the SOD of 68 inches. So now plugging all of that into the formula, I have a 2.2 centimeter measured nodule times the 68 SOD divided by the 72-inch SID. And so now my object size would be, everybody working the math problem? I'm working it right along with you. And the answer is 2.7 or 2.8 centimeters. Distortion. The last half of this PowerPoint, we're going to talk about some different types of distortion. So distortion is the difference between the shape of an object in an image and the shape of the actual object it represents the patient. So here's some examples of some hands. This is actually the experiment you guys will be doing in lab to demonstrate elongation, foreshortening, and motion. So let's start with shape distortion. So when the X-ray beam part and the image receptor are centered with the part parallel to the image receptor and the beam perpendicular to the image receptor, there should be no shape distortion at all. Off-centering of either the central ray or the part can result in the same effects as if you were angling the beam. So you could have some shape distortion just by off-centering the part or the beam. So here's kind of a picture of that. So I have the part off-centered from the beam, and I see elongation. Here I have the part centered on the beam, and it is representing the part appropriately. So then I have it off-centered in the other direction, and I'm going to now see foreshortening or shortening of the image in relation to the actual object size. So let's talk about elongation first. So angling or off-centering the beam against a spherical or cubical object causes elongation. If the beam and object with the long axis are equally angled to the image receptor, elongation distortion occurs. So if I have the beam and the object angled to the image receptor, I'm going to get elongation. If I have the image receptor and the beam, and I have equal with the object angled, I will get elongation. You're going to do this in lab, so it'll make a whole lot more sense when you're doing it. But make sure you pay close attention to these definitions when you're setting up your experiments. So here's the picture example of what I was just talking about. So I have the part and the central ray perpendicular to one another with the image receptor angled. It's going to show me elongation distortion. Second one is when a relatively flat or tubular or wedge-like object is tilted in relation to the beam and the IR. Foreshortening will occur. So here's our example. I have the beam and the IR perpendicular, and I'm tilting the part, and it's going to give me foreshortening. Same here, I'm going to get foreshortening. And what's interesting here, you notice this part of the bone, they're depicting as a much larger portion of the bone, and when I bring it farther or angle it up away from the IR, you're going to see magnification right along with that foreshortening. So it's very, very important that when positioning, you follow best what the book has told you, but you must look at your patient. Okay, must look at your patient, because I want to position accordingly by my patient body habitus, so that I will have minimal magnification. I will have minimal shape distortion. But again, sometimes we talked about sometimes you use angles to move other structures away from the structure of interest. So as you're going through your procedures class and you're learning about the angles of the different positions, think about why are they telling us to angle? What's the purpose of that angle? Not, don't just memorize the angle, but think about the actual purpose. What am I trying to move out of the way? How am I trying to get those particular bones in relation to the IR? What is it about that they have written that particular angle or that particular position of the body? When you get to the skull work, which I will do maybe in January or so, you'll get some of the skull work, maybe towards the end of this semester. But there are a whole lot of angles and a whole lot of positions that we put the patient in for various skull images, and it is really to get other structures away from the areas of interest. The mandible is a great example. If I wanted to see how the mandible is seated within the skull, I have to angle the head and angle the tube to get that image. So it's very interesting how you manipulate these factors to produce the image that you need. Motion. So motion is mostly bad. I do not want to have blurring of my image due to motion, unless I'm doing a breathing technique, okay? But in general, I want to reduce the motion as much as possible, because if you want to see a degraded image, you want to see an image with lots of fuzziness, lots of penumbra, then image something in motion. We'll do this in lab, and you will find out that it is so very difficult to capture emotion with our equipment, because it tries its darndest not to capture emotion. So you have to do some certain things to make it happen. And I'll let you give it a shot for a little while, and if you continue to struggle with it, I'll come out and help. So here's your line drawing picture, but I have this object that's in motion, and it's going to have an area of an unsharpness, and you'll see that in your lab work. All right, in conclusion, we have talked about a lot of different stuff here today. So make sure you go back over these terms. I kind of wanted to lay it down here in this last slide to kind of give you kind of an overview of the things that we've just covered. So we've talked about the stages of the image, the latent image, the displayed image. We've talked about the characteristics of each. Make sure that you go back and review all the definitions of these things. Make sure you understand the mathematical relationship as we're, making some of these changes, the SID, and when we're talking about the SID and the OID relationship and how we can reduce magnification and improve the sharpness of our image, all of those things. So, this was a jam-packed full of information. There's a lot of things that I want you to make sure you go and look at your textbook and review some of the definitions they've given you in your textbook, and review some of the definitions that I've given you here in this PowerPoint. Some of them may be a little bit different. Just ask questions. If there's something you do not understand, make sure that you ask lots of questions, because we will be doing this in lab on Tuesday and Wednesday of this next week. So make sure you have a good grasp of this material before you leave that lab session. Ask the questions that need to be asked. If there's something you don't understand, make sure you let me know. I will be recording a second PowerPoint that is just some of the math stuff. So look for that coming out soon.